Okay, welcome to Quantum 2. My name is Jens Paulsberg. I'll be your session chair, and we have two wonderful papers. The first paper is on automatic uncomputation, and the speaker is Kengo Hirata.
Right. Thank you for the introduction. So this is a paper about quantum computation. So let me review about the difference between the classical computation and quantum computation first. So in quantum programming languages, the data we use are different from usual classical computation. So first of all, in classical computation, we use sequence of bits as a data, which is just this, one or two data. And on the other hand, in quantum computation, we use qubits, which is just a linear combination of these bits. And for functions, programs, we can do like usual arithmetic function in classical computation, but in quantum computation, we have two basic operations you can do, which is unitary operation and measurements. So unitary operations are kind of usual computation, and measurement is a kind of projection from the linear combination to one sequence of bits. And for the type system, in usual classical computation, you can do anything, but like including copying resources or discard resources. But the main difference between classical 1 and quantum 1 are that in quantum, you cannot copy or discard, and it's called linear type. So let me look into this linear type in detail a little bit more. So in linear types, you cannot copy or discard. So the copy means, prohibiting copying means you cannot write the program at the top, which uses this x twice in the first line and in the second line, which corresponds to non-calling theory in quantum computation. And prohibition of discarding corresponds to prohibit a program which looks like at the bottom, which implicitly forgets this resource y, which corresponds to principle of implicit measurement. When you forget something in programming language, then that corresponds to implicit measurement. But we don't want to do measurement implicitly because it's kind of like a factorial operation. You don't want it to do it implicitly. So that's the point of linear types. But the problem is this prohibition of discarding is sometimes a little bit not very convenient. We sometimes want to allow kind of discarding. So let me explain what kind of thing happen in quantum computation. So the example I'm going to consider now is like this. And so we're given a built-in function end, which takes 3 qubits and outputs 3 qubits. And we don't do anything on the first 2 qubit bits, but we compute Q3 XOR Q1 and Q2. So if the input was 0, 0, 0, and then the output is going to be 0, 0, 0. But if the input was 1, 1, 0, then the output is going to be 1, 1, 1. And so this is the given function you can use. And the goal you have to do is to make a function, n3, which takes 3 qubits and outputs 4 qubits, which computes Q1 and Q2 and Q3. So for example, if the input was 1, 1, 1, then you want to compute 1, 1, 1, 1. So how to make this program? So this is the example implementation. And this takes 3 qubits, which has, So we have qubit types, and it takes 3 qubits and outputs 4 qubits. And what we have to do first is to introduce a temporal value, which is initialized by 0. And then apply AND to compute x and y. Next, in the next line, we introduce another qubit, which is going to be the return value, and compute x and y and z. So now we got x, y, and z, and we still have x, y, and z. So is the computation done? No, because we still have the temporal value, which has to be discarded. But you cannot measure this, so you have to reset this x and y in some way. So how to do that? To do this, one way to do this is to apply AND again here. And after applying this AND, so you get x and y, XOR x and y, which is 0. Now you got 0, and this 0 doesn't have any information like x or y, z, so you can safely measure this and turn this ket 0 to classical bit 0, and then it becomes a classical confirmation. And because classical information can be discarded at any point, so now, oh, sorry. Oops. Oops. Yeah, so you can now discard it, and you get the computation. So it's done. So this is how we implement this AND3 in linear type. But is this we actually want to do? Like, no, it's not like we don't have to measure this, because this measurement doesn't do anything. We just need to know that temporal value is reset to 0 here. And then we just wanted to just forget the allocation. We want to deallocate this temporal value. But now, this now violates the linear types, and we now have the verification problem here. So that's why we don't want to have like strict linear type in this concept. But what about this third line? This third line was only introduced to reset the temporal value, and the actual computation was only the first 2 lines. So let's say we also don't want to write this, but we expect the compiler to do this automatically. So that kind of system is called automatic uncomputation. So in a language which has automatic uncomputation, you only need to write first 2 lines and then forget this temp and expect the compiler to detect this forgotten temp and then reset it to 0 automatically. So let me summarize the concept of automatic uncomputation. So uncomputation is a way to drop resource in a safe way, in some way, yeah. And automatic computation is what does automatic uncomputation does is first detect the drop the batteries and verify whether you can actually reset it. And then if the compiler knows how to reset it, then we expect the compiler to do it. So we're now interested in what kind of verification we have to do here. So what do we have to do is mainly we have 2 points. First one is that because when we want to reset this temp, we actually need to use x and y again. So first point is that we have to have x and y still alive and unchanged when we want to drop this temp. So that's the first point. And the second point is that unfortunately, not every computation can be uncomputed, so we have to have some kind of restriction. And one of the sufficient restrictions is to know, is that what you have done to this temp is almost like Boolean circuit, which is classical computation. But this sounds like a strict restriction, but it's a kind of reasonable restriction. Right, so this is something we want to do in verification. And to make a type system for this automatic computation, what we want to do is to introduce a special type, sharp D, which means that you can drop something. But I mean, it has to be essentially linear, but in some way you can drop this. And what we expect in the type system is that we want to implement this AND prime, which takes 2 qubits and returns another qubit, which is droppable. And in this type system, this sharp D has to be a little bit weaker than linear type because it's allowed to drop. It's allowed to be dropped. But it has to be stronger than affine types because it can be dropped only until x and y changes. You cannot drop it unrestrictedly. So that's the point we want to do. And so here, we notice that we have to have the kind of notional time in our type system because we need to know the x and y, until x and y change part. And we also have to know that, the unchanged thing in type system. So how to do that? The solution we found is to use the type system in Rust and lifetimes. So lifetimes are just a kind of interval of program, time of interval, and it forms a posit. And with this lifetimes, we can make so in our type system, we introduced 2 special types, which is droppable, a sharp alpha, which means droppable until alpha. And we also need to have immutable reference, which means you can, it stays unchanged until some lifetime alpha. And now, what we want to have is the function n prime, which takes two immutable qubits and immutable references and outputs one droppable reference, a droppable qubit. And it has to have common lifetime because you need to match this time. So that's the idea. And with this lifetime annotated sharp type, this lies in between affine type and linear types. And if this alpha is the kind of longest one, which means that you can drop at any point, then it matches with the usual affine type. On the other hand, if the alpha is the kind of shortest one, which means it's already happened, in that case, this sharp alpha t means that you can never drop, which is going to be the same as linear types. So that's the idea of our type system. And what we have found out is that automatic uncomputation can be nicely represented by Rust and combining with basic quantum types and affine types with lifetime sharp alpha t. So, and we only explain a very easy example, but in general, we can the temporal value we want to drop can depend on a lot of other variables which has different lifetimes, but we found out that lifetimes can completely characterize the droppable thing. We also gave two operational semantics in our paper. And the first one is something we call simulation semantics, which is a kind of naive semantics of our language. But the problem is that this doesn't give you how to compile a program. For example, like this program, forget, takes one qubit, but immediately forget it. But so this means uncomputation, but the uncomputation depends on what kind of computation you have done on this X. So this forget function doesn't compile to a unique circuit. So that's the first simulation semantics. And the reason I call this simulation semantics is that you cannot represent it as a circuit, but you can represent it in a mathematical way, and you can simulate it in CPU easily. On the other hand, we also gave another semantics, which we call uncomputation semantics. And in this semantics, we interpret a program into a circuit graph, which is a kind of directed graph, which preserves all the history of the computation. And then in this directed graph, you can play a pebble game, which is a kind of game you can put a pebble on a node or take it out. And putting a pebble corresponds to do a computation, and taking it off is corresponds to uncomputation. And we found out that any strategy on pebble games give you actual computation. And we also proved that these two semantics are equivalent in some sense. So that's the point. That's the two semantics we gave. And we also want to talk about the related work. So the automatic computation governed by type system was firstly introduced by Silk, which is pretty nice work, which also has a CPU simulator, which we don't have it yet. But the type system was kind of ad hoc and was a little bit tricky. But in our work, we found out that the type system can be represented very nicely with adding sharp alpha t to Rust type system. So we also have lifetimes, which not only can be used to verify the uncomputability, but it can also be used to optimize the uncomputation. We also can have forget function, but this function doesn't type check in Silk. So that's the difference. So as a summary, we introduced a new type system for automatic uncomputation, which uses type system Rust and add one type, add a special type sharp alpha t, which is affine type, but restricted by lifetimes. We also give a lot of examples, And we also give two semantics. And we prove the equivalence of two semantics. And the interesting point of the second semantic is that we use Pebble games as a backend, which has been studied as a model of uncomputation, but like it was not like studied as a related to the relation between the programming language was not made clear. So as far as we know, this is the first language which uses Pebble games as a backend of our semantics. So that's the end of my talks. I would like to have some questions.
Okay, questions. We'll bring a microphone to you. Just raise your hand. First question over here.
Hi, thanks for the very cool talk. You mentioned that it's possible to automatically uncompute values that have been computed by classical computation.
Yeah.
In general, it's also possible to do this if you've applied phases like Z-gates or RZ gates. It's also safe to do those. Does your system account for such a generalization, or do you see any challenges?
Well, for example, like a simple counterexample is like if you add Adamar gate, then I mean, I have to do some mathematics to explain this, but Adamar gate, I mean, that's kind of very simple, like basic operation in quantum computation, but Adamar gate it's prohibited in quantum of this automatic uncomputation. But probably, yes, I'm thinking of like extending how to like, you mentioned like Y gate. No, rotation gate.
In this case, probably Z-gates or RZ gates would be fairly easy to support.
I mean, that's kind of future work. Yes, it hasn't been considered in our work, but that's a nice future work, I think.
Thank you.
Other questions? Over here.
It's a question by a non-specialist. Huh? So you say you can do this when you want or never. But there are many other possibilities in between. And why don't you use some temporal logic to express you cannot do it until you do something, and then if you do it before something happened, then it's okay, but afterward you cannot, or things like that. But temporal logic will allow you to express these properties. Would it be interesting?
Yeah, I think it's gonna be interesting. But the reason we use Rust is that we also need to have like the immutable reference, which is already built in it's already a part of Rust, and we found out like lifetimes can be fit very nicely with this. But probably there are a lot of other way to do like represent. We have to do something before something happens. I think that's, it's possible. I think it's possible to do it in another way. Thank you.
Question over here.
Hello. I have a question about, so I imagine you prove some kind of notion of type safety, right? So that your type system it preserves the semantics in a certain way. And I imagine you're taking like a syntactic approach here to prove type safety, like usually by progress and preservation. And if in this, if you take a semantic approach, how would you go? I would imagine it's a bit hard to prove that when you have a substructural type system, such as yours, which is, I think, is substructural, right? And if you have references, I thought like it's quite hard to prove this in a syntactic way, type soundness. Like maybe you can say a bit more about how you. Is there something to say about type soundness here?
Type sound. I mean, we have subtyping. What do you mean?
I mean, like proving that your type system is, obeys the semantics.
Yeah.
Like type safety, I mean.
Can I give an attempt at rephrasing?
Yeah, sure.
So I think he's asking, you have the type system, and we want a theorem about the type system that says that it's sound with respect to one of your two semantics.
Right. Yes.
Do you have this in the paper already, or is it?
I'm not very sure how to represent it, but like, I mean, it's not very functional. Then it's like it just like do one thing and one thing in each step, and type is preserved in some in those steps, but if you want to change the types, you have to. We have like a type coercion, which is because we have like subtyping, so you can do that. But I mean, you cannot do it implicitly in our theoretical paper, but I expect to have that in the implementation. I mean, we don't want to write every like type coercion explicitly in implementation, right?
I imagine it's some kind of progress preservation, but we can talk about it afterwards.
Yeah, thank you.
Yeah, definitely. Let's do that. One more question. One more question. Anyone wants to ask the last question of this part? Let me ask you, what's the largest example you have shown that type checks?
We did the Grover.
Oh, good.
Yeah, Grover algorithm.
Very good.
That's the largest one, I guess.
Excellent. All right. Thank you again.